So what does that mean? So over here we can see we have a photon, and the photon can be unpolarized, linearly polarized, or circularly polarized. Then we have a target. So we have X, Y, and Z. So for us, the Z direction is along the beam line. So it can be in the plus or minus Z, and the X and Y is basically in the transverse direction. So that would be the direction of the target polarization. Then we have recoil polarization, and then we have target plus recoil. So the target is polarized in a certain direction, and then so is the recoil polarized in a certain direction. So in the red box, these are what we can actually those are the observables we can access through pion production. But the interesting thing is with kaon production, which is what I'm doing for my thesis, you can access all of these. And so today I'll be showing you the F, T, TX, and TZ observables. And the reason that you can access all of these is because of the self-analyzing nature of the lambda, which has to do with the S and P waves and things like that. Okay, so, and as I mentioned, observables are really useful to help disentangle these partial waves because they're more sensitive than the cross-section data. Okay, so now I will talk about the experimental setup. So the Frost experiment, which is the experiment I worked on, was first approved in 2002. And it ran in two parts, 2007 to 2008, and that was referred to as G9A, and it had a longitudinally polarized target. And then it ran again in 2010, but this time it was referred to as G9B because it had a transversely polarized target. So the only difference here is the target's polarization direction. And I'm doing the second half, the G9B. So we used a butanol frozen spin target where the free protons are aligned within the target. We had a polarized photon beam. So we had it circularly, which is coming from a gold foil radiator, and then we also had longitudinally, which is coming from a diamond radiator. We had various electron beam energies from 2.3 to 5.6 GeV. Then I also which resulted in a photon beam energy of 0.5 to 3 GeV. So here you can just see Jefferson Lab at one time had the ability to go to 6 GeV, but because it's a photon beam, it is converted and we only get 0.5 to 3 GeV. So in G9B, we collected about 14 billion events. And the interesting thing, as I mentioned, is because of the self-analyzing power of the lambda, we can access all these beam target and target recoil observables, which had never been done before. Okay, so Jefferson Lab. So here's an overhead view of Jefferson Lab, which I said was located in Newport News, Virginia. And you can kind of see it, there's this, almost looks like a racetrack, but the accelerator is actually underground. So in the injector, which would be right around here, and in this schematic would be this green box. So in the injector, there's a laser, and the laser hits a gallium arsenide wafer, and it produces polarized electrons. The electrons are then accelerated around a linac, and then we have the dipole magnets in these curves that can help maintain the curve in the arcs. And it can be accelerated up to a maximum time of 5 times, which gives a maximum energy of 6 GeV. But currently we're almost finished with an upgrade, and the upgrade will allow for 12 GeV in energy. And then once it's accelerated around the desired number of times, depending on the experiment, then it can be sent into 3 different experimental hulls, hull A, B, and C. So then over here would be A, B, and C. And the hull I'm interested in is hull B. And then this upgrade, in addition to a higher energy we built, there was another hull build called hull B. So now, the electrons they enter hull B. So then what happens? What happens is in hull B there's a photon tagger. So the electrons come in and it hits a radiator. So for my portion of the experiment, it was a gold foil radiator. And so the electrons hit the gold foil radiator and brimstone photons are emitted. The photons travel along to the target, but the electrons do not. And the electrons are bent towards this electron dump here due to this tagger magnet, which is about 1.75 Tesla, up to. And once the electrons are bent down, there's 2 separate detectors. There's an upper hodoscope detector and a lower hodoscope detector. And the upper has 384 E counters, which basically has PMTs and scintillators, and it's measuring the energy of this scattered electron. Then the lower hodoscope, which has 61 T counters, again PMTs and some scintillators, this measures the timing of the electron. And the reason we want to know the energy and the timing is because then that's how we get the energy of the photon. So the energy of the photon is equal to the energy of the original, this beam, the original energy from the accelerator, minus the energy of the electron scattered. And that gives us the energy of the photon. And here, as I said, because we're using the gold foil radiator, that means the photons are circularly polarized. And that means the electric field is rotating about the momentum direction of this photon that's been created. Okay? So now class. So the photons come along, the electrons have been taken care of. Inside of class, there's a target, which I'll describe in a moment. But the photon interacts with the target and particles are produced. And so right around the target, we have a start counter, which gets the initial timing of the produced particles. Then we have here in blue the drift chambers, which can track the trajectory of the produced particles, and then we can also get the momentum of the particles. In red, we have these time of flight detectors, which get the final timing of the produced particles. And then we have in green this electromagnetic calorimeter, which can detect neutral particles such as photons and neutrons. And here in yellow, we have a toroidal magnet, a torus magnet, and depending on the setting of the magnet, it can bend the particles either inward or outward, depending on the experiment setting. So now the target. So this frost experiment had a special target designed for it, and it comprised butanol, which is an alcohol. So it had C4H9OH. So the butanol is dripped into a liquid nitrogen bath. It's cooled very low. Then the liquid nitrogen is removed, and then a liquid helium bath is put. So then when it's actually in the class, it's got the butanol surrounded by liquid helium. So here in the schematic, the purple is the butanol. So what happens is, before it actually gets entered into class and the experiment runs, a polarizing 5 Tesla magnet, a very large magnet, is put around the cryostat. This is the cryostat, the entire setup. And what happens is this 5 Tesla magnet aligns all the free proton spins in the butanol target, and it can align them to around 95% at 1 Kelvin, which is very low temperature. And then this rather large magnet is taken away, and then there's a holding coil. So this is the holding coil for G9B. The G9A target had a different holding coil because of the different target polarization. So here this holding coil is 0.5 Tesla, and it can actually help keep these protons aligned when it's actually in beam. So that would be the yellow part here around this butanol. In addition to the butanol, there's 2 carbon targets. And why do we need these carbon targets? It's because, as you can see here, this is not a pure hydrogen target. It has C4H9OH. So that means there are 74 bound nucleons and only 10 free protons, which means there are 64 bound nucleons that would contribute highly to the background. So this carbon helps to subtract this background. And when it's in beam, it's operated at 30 millikelvin, which is very low. And this target has a very long relaxation time. So here, this is over the course of the experiment. This is run number down here, so it's very hard to see. And over here is the degree of the target polarization. So we can see it's around 85% on average starting, and once a week it was repolarized because of this relaxation time. And that way we could have a pretty high polarization over the course of the experiment. Okay, and this is just the polarizing 5 Tesla magnet that was used. As I said, it's quite large. And this, so this is the cryostat. It's moved out of the center of class. The polarizing 5 Tesla magnet comes. Takes about roughly 1 to 3 hours to actually polarize. And then this is moved, and like I said, the holding coil is there to keep it, the protons aligned. Okay, so now the calibration of the data. So 14 billion triggers were taken during G9B, which resulted in about 36 terabytes of raw data. So before you can actually use this data for analysis, it has to be calibrated. And this is a group effort done by the entire collaboration of class. Well, okay, members of class are doing it. And what's happening is the raw electric signals are used to reconstruct 4 momentum vectors for these charge tracks that have been produced. So many iterations are done to get the correct information. And the part that Catholic was involved in is we did the tagger, which I had previously described, and also we did the time of flight calibration. And then we also did the cooking of the data, which means when all the data was finished, we could, when all of the data was finished and calibrated, we could then proceed to, reconstructing everything properly. So just to briefly mention the calibration of the tagger, since that is something I actually did work on. So what happens is we want to get the correct tagger calibration because that allows for finding the energy and the interaction time of this photon, which is crucial in reconstructing the events later. And this timing of the tagger has to match the response time of the accelerator. So basically what that means So here's one run 62707, and what you're looking at here is the timing of the tagger minus the timing of the accelerator. In theory, you would want those to be 0. You would want them to coincide with each other. So here's 0, and so you think, okay, for this run it looks okay. But at the end, in this T-counter bins, at the end, there's clearly a problem. So this needs to be calibrated, and this shows the after to show that now we have the correct timing match with the accelerator, which is important. So not only does the tagger time have to match the accelerator time, but it should match the reconstructed vertex of the other detectors, such as time of flight or the start counter. So here in this plot, we can see this is the start counter, which is where it gets that initial timing of the particles, minus the tagger time. And again, we would expect this to be around 0, and we can see that. So that is the zeros here. So again, that shows that the calibration of both the tagger and the start counter was performed correctly. Okay, so now we'll move on to some event selection. So now the calibration has been done, we've cooked all this data, so what happens now? We can skim the data for events of interest. So many final states can be realized, but the ones that I'm interested in is where gamma p, so the photon hits a proton, and a k plus lambda is produced. And then the lambda decays into proton pi minus. So that here I would detect a kaon and a proton. But also I can look at another reaction at the same time, which would be, again, the gamma and the photon interact, and it produces a k plus and a sigma naught. And here the sigma naught decays into lambda gamma, and then again the lambda would decay again into p pi minus. Okay? So now what I'm doing, you can see I'm identifying a proton and a kaon in both of these. And also, in addition to doing that, I identify one photon